This self-balancing camera gimbal, this robotic arm, and this planetary gearbox all have one thing in common. They rely on finely tuned PID controllers. PID is everywhere, in your thermostat, your car, even your coffee machine. But the truth is, most people just guess the values and pray it works. It doesn't have to be that way. You can either spend hours tuning or a couple of minutes if you know what you're doing. So today, I'm going to show you step-by-step how to tune your PID controller, all the essential terminologies, and how you can apply these strategies to your next robotic project. If you're new here, I've been doing robotics and AI for 10 plus years and have lots of resources on my channel, so go ahead and check it out. So for a lot of my robotics projects, I have a membership where you get to have select access to deep dive videos where I go into the details of my coding and design, and I have 30% off for all my course materials. And for the robotics lead, you get full access and you get 50% off. So go ahead and check it out. So this right here is a motor from MyActuator, and you can see I have the plots in my background nicely tuned already. So by the end of this video, you're gonna see how I'm gonna go through step by step to tune this motor to get some results like this. And you can see right here, I'm running it in sine wave, and you can also see the response plot is also pretty good. So I'm gonna explain all the details about this, so let's get started. So let me first explain the setup that I have. So in my hand right here, I'm holding an actuator from MyActuator. This one specifically is the X6-60. So this one with the features here, I'm just gonna read off the back. It's a 320 watt actuator. We have a 20 Newton meter rated torque. And then it has a dual encoder, which means that if you look at the motor, there's typically what's called the output. So the output has an encoder reading, so this is out. And then usually in the back where it attaches directly to the motor, this is the input of the motor. So we have encoders on the input and output end. This one goes up to 153 RPM, and it has a gear ratio of 1:20. So this is a pretty strong actuator. It has a planetary gearbox. It's great for robotics applications. But you can see right here, if you zoom in a little bit, you can see right here they have the black and red cables. These are the power cables. And then we have the CAN cables. Okay, so real quick, let me just explain my wiring setup here. And if you're not interested in this part, you could go ahead and skip on. But just to give you a quick overview, I have a motor here. So we have our power. This is my red and black line. So red is my 24 volts, and then my black line here, this is my ground. So all of this is connected to my power supply. So I have some power supply here. I also have a link, my Amazon store, also my YouTube websites links. You could just go ahead and check it out. But my power supply here is also feeding 24 volts. And then right here, I have my PC running Ubuntu here. So Ubuntu, specifically, I'm using 22.04 Jammy. So I have a CAN to USB device here. So CAN-USB. This is a device that can read the CAN message. So my motor also has a CAN high here. And we have a CAN low. So these are the signal for communication. This goes directly to my CAN to USB. And then we have a USB device that goes directly to my PC here running Ubuntu. So this is my setup here. And everything inside Ubuntu here, I am running ROS. Okay. So I notice my head is kind of blocking that part, but let me just scroll up a little bit. So you can see everything inside Ubuntu, I am running ROS here. So I have ROS on my channel, so if you're new to ROS, go ahead and check it out. But all of my code for my ROS is gonna be on my website. So see my pinned comments for the code if you want to run everything that I'm using today. So I have everything in ROS set up. So the way my ROS setup works is I have a launch file here. So my launch file will automatically set up a couple things. One is my plot juggler. So this plot juggler is what I use for viewing my plots, and then it spawns off RQT. So this is what's gonna let me view my graphs. Set my parameters here, my params. So these parameters is what I use to adjust my PID gains. Okay, and then lastly, I have some stuff that activates my ROS2 controls. So this is what's going to actually talk to my motor. So all of the code and package I already prepared and set up. So you could go ahead and check it out if you want to run this exact same demo. But if you want to tune your controllers, you're not limited to ROS. You could use anything you want. But for me, ROS with all the built-in plots and everything makes it really easy for me to use. So you can see right here, this is my plot juggler running. Nothing is being set right now. All my gains are 0. But you can see right here on the top here, I have a square wave running. And on the bottom, I'm monitoring the torque. So let me first explain exactly what these plots mean and why we're doing this. Okay, so the idea is we have a square wave, right? So we have a square wave that's continuously feeding it. So this is what we call, this is our desired position. We're telling our motor that, hey, motor, go to this position, and it tries to get there. And depending on how it get there, that's what we call the response. So first off, we set a lot of terminologies here. So this right here is what we call a square wave. And usually the square wave is going to be what we set to be our set point. So basically, set point, you could think of it as your desired position. So we have a position that we wanted to get to, okay? So you might be wondering, why are we using a square wave? So the idea of a square wave, if you have to go back to the classical controls, but I'll assume the audience has no knowledge of that. So I'm just gonna give a very brief background on it. So the main idea of a square wave is you could look at these steps here, right? You have a step that's a high, you have a step that's a low. So this part is like low and high. So the idea of repeating this over and over again is because in practice, what we really care about is the step response. So we have this term called step response. The reason why we care about step response is because in classical controls, this is the way you characterize a system. So the idea of a step response is if you hit a system, what is the behavior of it if you were to measure it? So the equivalent of this is how you would do it for a motor, is to give it a command that goes from, say, 0 to some new angle, in our case, maybe like 0.2 radians. So you give it a desired command, let's say 0.2, probably something smaller. Let me see what I set it at. So here specifically, I made it a little bit high, like 0.5, but you could play around with the values to see what's reasonable. Usually smaller step responses might make more sense. So in this case, I kind of made it a little bit messy here. Let me just redraw it. But let's say you have some value of like 0.1. Again, this is going to be experimental based on what you're doing, but you have a step, and that's your step response. So this is your desired position. And depending on how it gets there, this plot here would be your measured position, and that would be your response. So essentially what we're doing is we're always telling it to go here, and we read the response. So we want to do this repeatedly. So every time we update a gain, we want to see if the response has changed. So the way to do this repeatedly, one way is to stop your system and then give it a new command. Stop your system and give it a new command. As you can see, this is a very repetitive process. So instead of repeating this over and over where you stop and start, what people came up with is, oh, why not just repeat this wave by, first sending it one direction and then sending it a different direction. So this is where the idea of square wave came from, okay? So that's the whole idea of square wave. But then in practice, we don't usually move our system using a square wave. So we typically have our system follow something smooth and continuous. So that's what we call a sine wave. Okay. So in practice, the sine wave is our main objective to see if it's following correctly, because sometimes you can have a system where, okay, it's like following a step response, which we'll see in a little bit, but maybe the square wave following is very poor. So you might have a desired position that's what you want, but then the measured has really bad lag and it's really bad, so you might have to retune it, which we'll see in a little bit. Okay, so far we covered some main terminologies here. We have square wave. This is what allows us to see our step response, and given our step response, this is typically whether we have our set point, which can either be a sine wave or a square wave. So usually our desired position plots can fall into the two categories that we just talked about, the sine wave and then the square wave. Okay, so these are our two desired positions. But basically, we're always looking at a desired and measured position, and we go from there. So if you're looking to 3D print something but don't have a 3D printer, make sure to check out PCBWay, the sponsor of this video. Come up here to CNC 3D printing, choose 3D printing. It's really easy. Go ahead and drop in your STL files here, choose the quantity, your units, material, color, process, and so on, other things like threads if you need it, and go ahead and submit your part for review, and in a few days you should have your parts. So I want to dive a little bit deeper into the step response. So typically here you can see this is our square wave or part of a square wave, and we're saying, okay, motor tries to get here. So a couple things that you typically do to characterize your step response, what people look at is if we just draw a sample plot here, this might be an example response plot. So typically, we have what's called the rise time. So there's a specific definition which you could look up. I'm just going to explain rise time in a more practical sense, because unless you're getting down into the nitty-gritty, very tight performance requirement, you're going to have like some percentage, and then you're going to see what time it gets there to reach that percentage. But generally speaking, from a more practical standpoint, rise time is just really a characterization about how steep the slope is. So you could have something that response is very fast. So the faster the response, meaning the slope is steeper and steeper, then the higher the rise time. So that's more of a intuitive conceptual understanding of rise time. Again, you could go ahead and find the exact percentage to have the exact characterization of it, but a lot of people in practice that's doing very rough hands-on tuning don't really go down to that level of detail. So if you're looking into that level of detail, go ahead and look it up. Okay, so in general, the quicker the rise time, the less lag you'll have. Okay, so that's for rise time. The second important characterization is what we're going to call overshoot. So if we look at the plot here, overshoot is the amount that goes over your desired position. So this is what we call overshoot. And typically, a little bit of overshoot is bound to happen if your rise time is very fast, because that's just the nature of how your system behaves. So it really comes down to what system and what performance metrics you're shooting for. So I would say a very small overshoot tend to be acceptable if you really want to prioritize a quick rise time. Okay, and then the second part that you'll look at is this distance here. So this is measured as your desired and measured, the difference between your desired and measured over a longer period of time. Again, there's some formal definition of where that cutoff starts, but in general, more practical standpoint, you just typically look at something that's past, like a second or something, then the amount of error that you see during that time is what's called your steady state error. Okay, so these are the core terminologies that you'll be using: the rise time that we said, overshoot, and steady state error. So once you have all three of these things reach somewhere around what you want your system to look like, then you would call your tuning done. Okay, so let's take one step back to see what it actually means to be using a PID controller. Okay, so first off, the terms here, the P is proportional, and then the I is integral, and then the D is our derivative. So this is what it means to use a PID. So you're essentially having three knobs that you can turn, also what we call gains. So these are parameters that you can adjust that will change the behavior of your system. So if we look at it from, missing an L here, if you're looking at it from a control and block diagram standpoint, typically what this will look like is here we have our desired position. Okay, so again, this could be either your sine wave or it could be your square wave. So depending on what your desired input is, you have one of the two, and then you feed into what we call a sum block. This is going to have a plus and minus. So inside of here, you're going to pass in your error. So your error is going to go inside what we call our PID controller. So inside our PID controller, I'll briefly cover the equations in just a little bit, but the output of your PID will go to your system or your motor. So I'm just going to put motor in our case because we're dealing with a motor. And then the output is going to be your measured position. Sometimes you'll see it as P, and then you're going to see a subscript here as P measured. Same thing with the desired here. Sometimes you'll see P here as P for position. So P is position here. And then you have a feedback. Typically, this is read from your encoders, and this will go back to the sum block here. So this is a typical structure of a position controller. So specifically, the output of your PID here would be current. Sometimes, depending on how your system is set up, it could be torque, and you have to convert it later to actual current for your motor. But in our case, we're sending a current command to our motors. So this is the basic setup that we have here. And then you can also have more complicated ones. So you could have a position, velocity, cascaded type loop where you have an inner loop, which I won't talk about in this video, but that's a more complicated tuning process where you have to tune the inner loop and then the outer loop. I'll probably have a members only video for this topic. For those that are interested, make sure to join my membership. But in this video, we're just gonna have a direct, position current only loop. So this one you might hear as position velocity or position velocity current loop. The current loop part we're not going to touch. This one is already tuned inside the motor driver. So we're only going to be touching the outer loops here. So in our case, I will be demonstrating tuning the position loop. So this is a general structure of your controller here. And if we dig a little bit deeper into the PID block here, what this block will actually look like is usually the output, in this case, I said it was current, right? But sometimes you'll see the variable U for output. So if we have our PID here, simply you could look at it as, our input is error and we have some control output. I'm just going to call U here. So this is the general inputs and outputs of our PID here. So if we look at the equation, what we have here is U is going to be Kp times E. Again, E is my error. You're going to have another variable called Kd here. This is going to be multiplied by E dot. So this is my error derivative. And then we have Ki times the integral of our error. So here, this is our P gain. You're going to see it as Kp or P gain. This is our proportional gain. This is our D gain, our derivative gain. And again, this is our error difference in our error dot. Again, that's your derivative of your error. So derivative of your error. And then this Ki here is our integral gain. And this right here is going to be the cumulative error. So that's represented by the integral sign. So this whole term here, I'm just going to call cumulative error. Okay, so this is a structure of the PID. So essentially when we play around with these Kp, Kd, Ki gains, this is essentially what we're adjusting. So a common question that I hear or get a lot of times is, hey, Kevin, you have inputs of position error, which in our case, maybe it's radians or degrees. How is it possible that our outputs U is torque or current? How is that possible? So I get this question a lot, and the answer is quite simple. KP is, you could think of it as a unitless number, and not exactly unitless, but a unit that could be anything. So I don't really want, when you tune it in like your setup, you just put a number which you think is unitless, but really you could think of KP as any conversion that can convert any input to any output. So in our case, if our error is radians for the error, which is unitless, and if our KP is something that's going to end up converting it into current, then yeah, our units here is going to be amps here. Okay, so depending on what your unit conversion is, then you're going to have something that ends up canceling out for you so that your unit makes sense. Okay, so that's the general idea about the units. All right, so enough of the theory. Let's get into the actual tuning. So here I'm holding my actuator in my hand. Ideally, you should probably have this mounted, but I don't have that set up yet, so I'm holding it in my hand here. And again, make sure you have all your safety set up, like your e-stop. Right now, I have my power supply that I can quickly turn off the output by pressing a button, so I have my safety set up. But make sure to take safety as your #1 priority because you never know what might happen. So again, please take your precautions when tuning because if you're dealing with a big motor, it could get pretty dangerous and you might hurt yourself, okay? So let's go ahead and start tuning. So right now you can see right here in my screen, all of my gains here are 0. And I'm just gonna go ahead and choose some value here. So my mouse is acting a little bit funny. I think probably because where I put it here, but anyway, if I just choose some value here, let's set it to 1 here. So if I hit enter, okay, so you can see my motor is starting to move, right? And at first glance, you might be like, oh, look, it's moving and it's kind of following the square wave here. So you can see, it has some steady state error here because I can see a little gap between the blue and red. And you can see the rise time, the slope here is not too sharp, meaning that it's not very fast. I'm going to do like 1.5 here to be a little bit faster. You can see that by doing it at 1.5, the overshoot here is much higher. So I know that part is not too good, not what I want. So sometimes to smooth that out, you could adjust the D gain here. So I'm going to adjust this a little bit to say like, 0.2. Okay, so you see that this dampened it by a lot. And you can see it probably damped it too much because now it's not even reaching my target. So if I decrease this a little bit to 0.1, then you can see that it gets a little bit closer. So you might look at this plot and think, oh, it's actually kind of following the square wave. So you might think it's pretty good, right? So this is where you might want to jump into the sine wave to see how it responds. So I'm going to go back here to my wave publisher, and then I'm going to change the square wave here to a sine. I'm just going to delete this and then enter sine. So this will switch to a sine wave, right? You can see that even though the square waves seem to be behaving okay, the sine wave is actually horrible. You can see how poorly it tracks. You can look at the blue. This is my desired, and then the red is the red is the desired, the blue is the measured. You can see how poorly it tracks here with this large error. It doesn't even look like a sine wave. It's just some weird step. And if I were to hold this motor still, you can see that it's exerting very little torque. So it's actually not very good to handle external disturbances. Okay. And the reason why I'm monitoring the torque here is because I'm interested in seeing how much torque it's applying. So now that I see the poor performance, sometimes you can actually tune it too by just tuning it using the square wave, which I'll do here. And you could start ramping this up here. So for example, if I change this to, let's see, So I'm going to delete this and I do something like 11, for example. You can see that it's kind of following, right? But you can see that it's shaking a lot, okay? So I'm just going to ramp this up to something higher, maybe like 25 to see what happens. So you can see it starts oscillating, right? It's hard to see the motor moving with my hand holding it, but you could kind of see the motor is, again, the shaking is a little bit hard to see. You can see in the plots more, but you can see it's shaking here. And what the D gain will do, intuitive way of thinking about it, is it will smooth it out. So, you know, if I slowly increase it, I have like 0.2 here. You can see the ripples decrease a little bit. If I go to 0.3, it's starting to smooth it out a little bit. So if I go to 0.4, you can see here that it's starting to smooth out, right? It's looking better and better. If I go up to 0.5, so you can see around 0.4 to 5 is kind of the sweet spot. And now you kind of see the sine wave is following. So I'm going to go ahead and come back to a different wave. So I'm going to go to the square wave again. Come back here to sine. Type in square. So you can see this is my square wave response here. And you can see it's really snappy. The rise time, see how quickly it rises. So that means it's a fast rise time. You can see there's a bit of an overshoot. But again, that's the trade-off for a fast rise time, like I said earlier. And I could go back here to the gains again. And you can see that you could play around with the KD. So if it's a little bit, if the D gain is a little bit higher, you can see that it will overshoot a little less. But now there's some weird vibration that you see. So from that, you can see if I were to increase this a little bit more, you can see it starts dampening it, right? So from this plot, you can see that I don't have too much steady state error here because it's reaching the desired value. So I'm not going to play around with the I gain. But usually what you want to do is just simultaneously increase P and D together until you get a response that you want. So I could dampen it even more if I do a 0.6. You can see my overshoot is a little bit dampened now, so it doesn't shoot up as much. So I would say this plot right here is a pretty good response plot. And I could, for example, if I take out the D gain completely, you can see the effect of the D gain. So you can see the oscillation here. This is with no D gain. You can see it's shaking like crazy. Now, if I put back my D gain, you can see that the D gain will dampen out my system. Okay, so this is behaving pretty smoothly with a fast response time, typically like how I want my motors to be tuned. Okay, so if you want better performance, you might want to add a velocity loop, which I'll talk about to my members. So go ahead and check it out if you're interested. Okay, so I hope you found this video helpful. If you did, give a like and subscribe, and I'll see you in the next one.